Hi, this lesson is about solving systems of linear equations. Remember, a linear equation can be expressed in one of two ways. First way is what we call slope-intercept form, y equals mx plus b, or this general form of ax plus by equals c, where your x and y variables are on the same side. But make sure that your x and y's are only raised to the first power. If you have an x squared or a square root of y somewhere in your equation or something like that, it wouldn't be considered linear. So when solving a system, you're trying to find the solution to two linear equations, and there are three possible scenarios. So in the first scenario, we call this an independent system. This is a system where two lines intersect at a single point. The point of intersection is called the solution to the system. So a picture of what an independent system would look like would be something like what you see here. We have one line and then a second line, and the one point where they intersect is the solution to the system because it's the only point that both lines share. Another scenario is scenario 2. This is called an inconsistent system. This is a system with no solution. That is, the lines never intersect, and therefore they must be parallel. So here's a picture of what that would look like. We would have two lines. Remember, parallel lines have the same slope. They will never touch, and therefore, because they have no common point, there's no solution to this system. And then the third scenario is called a dependent system. A dependent system is a system with an infinite number of solutions. That is, the two lines are in fact the same line. So although when you state them, they might look different, they might have different coefficients and so forth, when you actually plot them, one line sits right on top of the other line, and so the graph would look like just a single line. Therefore, every single point that makes up this line, and remember there's infinitely many of them, that's why we have arrows at the beginning and at the end of the line. That's because it goes on and on forever, and every point that is represented on this line would represent a solution to the system. Okay, so let's figure out how to solve these. We're actually going to learn two methods to solve a system of linear equations at first, and then we'll learn a third one. But for now, we're going to focus on the substitution method and the addition method, also called the elimination method. That really depends on the author. So let's do one by substitution method. So here's our first example. We want to solve this system, y equals negative x plus 1 and 2x plus 3y equals 5. So just for convenience, I'm calling this equation 1 and the second one equation 2. So by substitution, it means that you are substituting one equation into another. So because equation 1 is in slope-intercept form, it's easy for me to substitute equation 1 into equation 2, which means replace the y in equation 2 with negative x plus 1. That's what you see right here. Once you make that substitution, you have one equation with only one variable, and your goal is to solve for that variable, which is x here. So you distribute in this line, combine like terms in the third line, and then you want to subtract 3 from both sides, which gives you the fourth line, negative x equals 2. And then when you solve for x, multiply both sides by negative 1, you get that x is negative 2. When you're solving a system, you should have both an x and a y value. So then you substitute negative 2 into one of the original equations, one of these. And it's just easier to work with the first equation, which is what you see here. So y equals negative 2 plus 1, which gives you a value of 3. So your solution is the coordinate negative 2, positive 3. When you get a single answer for both the x and the y values, that's what we consider to be an independent system, one solution. Remember, that's the point of intersection for these two lines. Okay, let's do another example, also by substitution. We want to solve the system and graph both lines, so that way we can see the graphical interpretation as well. So we have our two equations right here. The first one is 2x plus y equals 3, and the second one is negative x plus 3y equals 2. Okay, so we have to decide which equation we need to solve and for which variable. And again, it doesn't matter which one you pick. So I'm choosing to solve equation 1 for y. And when you do, you have to subtract 2x from both sides. And so you get this equation in slope-intercept form, y equals negative 2x plus 3. And then I'm going to substitute it into equation 2. So that's what you see here. So we have negative x plus 3 times negative 2x plus 3 equals 2. Then distribute the 3, which is what you see in this line. So we have negative x minus 6y plus 9 equals 2. Combine like terms in the next line to get negative 7x plus 9 equals 2. Then subtract 9 from both sides. We get negative 7x equals negative 7. Then divide both sides by negative 7, and you get x is equal to 1. Once you know that x is equal to 1, you can substitute it back. So I'm choosing to substitute back into here to solve for y, which is what you see here. So we get a solution of 1, 1. So that means that 1, 1 is the solution. It's an independent system, and it's the point of intersection on the graph. So let's actually graph these two equations. I'm going to graph equation 1 in blue and equation 2 in green, just so that you can distinguish them. And the point of intersection seen here is in red. Okay, so the first equation in blue is 2x plus y equals 3. Remember, that's the same as y equals negative 2x plus 3. All right, so I have a y-intercept at 0, 3. I have my point of intersection at 1, 1. And I'm just going to pick one other point. And again, you can pick anything you want. So I'm going to let x equal 2. And when x is 2, y is negative 1. So the points 0, 3, 1, 1, and 2, negative 1 are what you see here. Here, and then my point of intersection in red. Connect those points, and you get the blue line. Right, so let's do the same thing with the second equation, which is the one in green. Remember, the original equation was negative x plus 3y equals 2. If I solve it for y, I get y equals 1/3 x plus 2/3. So I have a y-intercept at 0, 2/3. I have my point of intersection, which is the solution at 1, 1. And then I'm going to plug in some other value. I'll pick 3. And when x is 3, and you plug it in here, you get 1 2/3 as your y value. So those 3 points get plotted on the graph. And so here's the 0, 2/3 is right here. The point of intersection is here, and 3 and 1 2/3 is right here. So you connect those 3 points, and you get the green line. So this is a representation of a system that's independent with a solution at 1, 1. Okay, so we're going to do the next couple of examples by the addition method, remember, also called the elimination method. And the reason why it's the same method called two different ways is because you are adding two equations to eliminate one of the variables. So here's our first system. We want to solve 3x plus 7y equals 22. I'm going to call that equation 1. And 4x minus 3y equals 17. That's equation 2. So again, your goal is to add equations 1 and 2 to eliminate one of the variables. So suppose I decide that I want to eliminate the y variables. You can choose either x or y, but you have to choose one. So since I chose y, I have to consider what is the common denominator or the lowest common multiple for 7 and 3. Why 7 and 3? Because those are the coefficients of my y variables. So the LCD is 21. So that means I have to multiply equation 1 and 2 by whatever number is needed to get 21 in the second position as the coefficient of y. So that means I have to multiply equation 1 by 3, and equation 2 by 7. So that's exactly what is being done here. My new equation 1, when you multiply it by 3, is 9x plus 21 equals 66. And my new equation 2, when you multiply it by 7, is 28x minus 21y equals 119. So now I'm ready to add the two equations. When you add equation 1 and 2, your x's become 37x. Your y's cancel out because I have 21y and negative 21y. And my constant on the right is 185. When you divide both sides by 37, you get your solution of x equal to 5. But again, you need to solve for both x and y. So you take x equal to 5 and plug it into either equation 1 or 2. I picked 1. You could pick 2 and you should get the same answer. So 3 times 5 plus 7y equals 22. So that's 15 plus 7y equals 22. Subtract 15 from both sides and you get 7y equals 7. Then divide by 7 and you get that y is equal to 1. So this is another example of an independent system because I get a single solution of 5, 1. All right, let's do another example with the addition method. Should it be here? Okay, so we have to solve x minus 3y equals negative 5. I'll call that equation 1. And negative 3x plus 9y equals 12. That's equation 2. So as I mentioned before, you need to eliminate one of the variables. So this time I want to eliminate my x's. And in order for me to eliminate my x's, I need for that first term to be 3x so that it will cancel with negative 3x. And the way to do that is to multiply equation 1 by 3. So that's what I did on this line. Multiply equation 1 by 3, you get 3x minus 9y equals negative 15, and equation 2 I just copied down. So that's negative 3x plus 9y equals 12. Well, when I add these two equations, something unusual happens. Both my x's and y's cancel, so the left side is just 0, and on the right side, negative 15 plus 12 gives me negative 3. When you get an odd result like that, where you have no variables and two different numbers on the each side of the equal sign, that's actually not true. 0 is not equal to negative 3. And when that occurs, you can safely say that there is no solution to this system. That's considered to be an inconsistent system, meaning these two lines are parallel. They'll never touch, so there's no solution. Right, let's do another example. This time I want to solve 2x minus y equals 1 and 8x minus 4y equals 4. Again, I'm going to use the addition method or elimination method, and I want to eliminate the y variable. So to eliminate the y variable, that means that I have to multiply equation 1 by negative 4, and so that's the new equation 1 that you see here below. So I have, when I multiply by negative 4, equation 1 becomes negative 8x plus 4y equal to negative 4. And equation 2, well, I just copied that down as 8x minus 4y equals 4. When you add equation 1 and 2 to get this next line here, well, this time everything cancels. The x's, the y's, as well as the constant. So you get 0 equals 0. That actually is true. So when you get a result like that, that's considered to be a dependent system, meaning you have an infinite number of solutions. So the tricky part about dependent systems is knowing how to express an infinite number of solutions. So to express an infinite number of solutions, you're going to let your first variable in your solution be x, or whatever you're told to let x be. So for now, let's call it x. And your y, well, you have to take one of the first equations that were presented and solve it for y. So I'm going to pick equation 1 just because the numbers are smaller, but you could do the same thing with equation 2. So I'm going to take equation 1 and solve it for y. In other words, put it in slope-intercept form. So when you do that, you get that y is 2x minus 1. So that's what you put in here for the y coordinate. So every possible solution can be represented by the solution that you see here in the box, is that your coordinates are x, comma, 2x minus 1. All right, so we're going to talk about determinants, because if you understand determinants, we can actually solve systems of linear equations by another method, which I'll talk about in a few minutes. But a determinant is a quantity, it's a scalar that's organized in what we call a matrix. Matrix is going to look like an array of numbers, or like a box of numbers where you have rows and columns. So if we let A equal the matrix A, B, C, D within these vertical bars, this is not an absolute value system. This is not an absolute value. It's considered to be a matrix. And when you're taking the determinant, or the value of that matrix, well, then you're multiplying A times D and then subtracting B times C, which is what you see here. So the value, or the determinant, the scalar quantity of a matrix, is the product of A times D, so you're multiplying on a diagonal, minus B times C. All right, so we call this matrix a square matrix because you have the same number of rows and columns. This one happens to have 2 rows and 2 columns, so we call this a 2 by 2 matrix. You always put the number of rows first and the number of columns second. So let's evaluate the determinant of the following matrices. So I have matrix, the matrix here, which has row 3, 5, and negative 1, 2. So the determinant of it is 3 times 2 minus 5 times negative 1. So that's 6 plus 5. So the determinant, the value of the matrix is the determinant value of 11. Let's do the same thing in part B here. I want to find the determinant of the matrix with row 4, negative 2, and 1, 5. So when you multiply across, you have 4 times 5 minus negative 2 times 1. So that's negative 20 plus 2. So this has a determinant value of negative 18. Okay, you can also use a matrix and its determinant to solve the matrix. So we want to solve the matrix with row 2x, 1, and the second row of 3, negative 1 equal to 5. And so we want to solve for x. So 2x times negative 1 is what you see here, minus 1 times 3, which is what you see here. So negative 2x minus 3 equals 5. Then we want to solve for x by adding 3 to both sides, which you get negative 2x equals 8. Divide both sides by negative 2, and you get that x has a value of negative 4. All right, so let's identify the dimensions, meaning the rows and columns of the following matrices. So there's 3. So A, this is a matrix with 2 rows and 3 columns. So this has a dimension of 2 by 3. Part B has 3 rows but 1 column. So this has a dimension that is 3 by 1. And C has 1 row and 4 columns. So 1 row is 4, 0, negative 1, and 7. And 4 columns, 4, 0, negative 1, and 7. So that dimension is 1 by 4. These are not square matrices because the number of rows and columns are different. So we want to identify the term in row 2, column 3 in the following square matrix. This is a square matrix because it has dimensions of 3 by 3. And if I look at the second row and the third column, well, then that's the value of negative 4, which you see here. Okay, so once we understand how to evaluate or find the determinant of a matrix, then we can learn another method to solve a system of linear equations, and this is called Cramer's rule. So if you have a system of two equations and two unknowns, so my two unknowns are x and y, and this is my system right here. A sub 1 and b sub 1 are the coefficients of x and y respectively, and my constant on the right is c sub 1. And my second equation has coefficients a sub 2 and b sub 2 respectively, with a constant on the right of c sub 2. So the following rule will allow me to solve for both x and y. So let's talk about the denominator too. The matrix in the denominator is just the coefficients of your x's and your coefficients of your y's. The x coefficients go in the first column and the y coefficients go in your second column. So in exactly the same order that you saw in your system. So the difference in the matrix in the numerator is that your x column gets replaced by your constants on the right, and that's because I'm solving for x. Your y column stays the same. So to solve for y, your denominator is the same. So notice here that the denominator to solve for y is still a sub 1, b sub 1 in the first column, in the first row, and a sub 2, b sub 2 in the second row. But what's different is the matrix in the numerator. Matrix in the numerator, because I'm solving for y, it means that your b's get replaced by your constants. So opposite of what we did when we solved for x. So the first column stays the same, but the second column changes to constants of just c. All right, so let's use Cramer's rule in order to solve an equation. And this is the same equation we did earlier with the addition method. So I have 3x plus 7y equals 22, and 4x minus 3y equals 17. So first let's set up our matrix in our denominator. The matrix in our denominator is just the x column, 3 and 4, and the y column, 7, negative 3. That's exactly what you see here. So when I evaluate that matrix or find the determinant, that's negative 9 minus 28, which gives me a value of negative 37. Now I have to do the same thing, evaluate the determinant of the numerator, but the column that gets switched out is the first one, and that gets switched with the constants. So I put 22 and 17 in my first column, and my second column stays the same as 7, negative 3. Then I evaluate the determinant of that matrix, and that's what we get here, negative 66 minus 119. That gives me a value of negative 185. And when you divide negative 185 by negative 37, I get a value of 5. So that's my x value. But remember, you have to solve for both an x and a y. So my determinant for y in the denominator will be exactly the same. 3, 4, and 7, negative 3 as my columns, and that gives me a value of negative 37. But now I have to come up with a new matrix in my numerator. And because I'm solving for y, you replace the second column by the constant of 22 and 17. Then you cross multiply to evaluate the determinant. So we get 51 minus 81 here. And when you subtract, that's negative 37. Divide that by negative 37 and you get a y value of 1. So your solution is 5, 1, which is the same solution we found earlier by the addition method. All right, let's do another one by Cramer's rule. So I have equation 1, which is y equals 2x plus 3, and equation 2, which is negative 4x plus 2y equals 8, first you have to rewrite equation 1 in standard form, which means move the x over to the left and write it first. So that's what you see here, negative 2x plus y equals 3, and equation 2 remains the same. We just copy it down as negative 4x plus 2y equals 8. So now we're ready to set up our two matrices. The matrix in the denominator will be the same for both x and y, and that's just the coefficients of the x's in the first column and the coefficients of the y's in the second column. And then I'm going to set up the matrix for the numerator, and that just means that you replace the first column by the constants, which goes right here. When you evaluate the matrix on the top and the bottom, you get the result of negative 2 over 0. Whenever you get 0 in the denominator, that's going to result in something unusual. It's either going to be an inconsistent system or a dependent system, and the way you determine which is which will depend on what you get in the numerator. So if you get something different than 0, like negative 2 over 0, that's going to be an inconsistent system, meaning no solution, meaning these are two parallel lines that we'll never touch. All right, so let's do another example by Kramer's rule. Here I have two equations, so 6x plus 9y equals negative 3, and negative 2x minus 3y equals 1. First set up your denominator, which is just the coefficients of x and the coefficients of y in exactly that order. So you write 6 and negative 2 in the first column, 9 and negative 3 in the second column. So when you evaluate that, you get negative 18 minus negative 18, which gives me a denominator of 0. Remember, whenever your denominator is 0, that's not going to give you an independent system or a single solution. So now we have to see what's going on in the numerator. So in the numerator, we want to replace the first column by the constants. So that's what you see here, negative 3, 1, and the second column stays the same as 9, negative 3. When you evaluate that matrix, your determinant is also 0. And when you get 0 over 0 with Kramer's rule, that's going to represent an infinite number of solutions, which is considered to be a dependent system. So the tricky part about dependent systems is how to represent the solution. So that means that your first coordinate is going to be some value, which could be x, but this time we're going to force x to be a. And it really, you could call it anything you want, like t or k. But suppose I let x equal a, then you have to figure out how to represent your y values. And you represent your y values by solving one of the two equations at the beginning for y. And it doesn't matter which one you pick, so I'm going to solve equation 2 for y. And if you do that, you get that y is negative 2/3 x minus 1/3. So your solution, or your solutions, I should say, because there's infinitely many, is the set of a, comma, negative 2/3 a minus 1/3. Okay, so now you're ready to try section 10.1, try the homework, and any of the methods that we use, substitution, addition method, or Kramer's rule will work to solve the systems. So good luck.